Harnessing Energy from Heat, Brennan Guerin. Harnessing heat energy is the future of energy sources. Heat is wasted in so many different ways, including industrial process, power plants, cars, and even body heat. The most practical way of harnessing heat is through the use of power cards, and that is you'll learn about towards the end of the presentation. I believe wasted heat will soon become the source of energy everyone turns to. How to power the world. There are many different ways to provide all the power we need to the world. These include solar, wind, and water to produce energy. However, there's one kind of power source that is commonly overlooked, and that type of power is harnessing heat energy. Heat energy is an excellent option for powering the world. All we have to do is start harnessing it. According to Jeffrey Marlowe, heat is a persuasive consequence of the reactions that enable modern industrialized life. Simmering power plants, hot light bulbs, the flame of a stove, and nearly all these processes that generate energy, heat emerges as a byproduct. Some of this heat can be power useful reactions, including Industrial Revolution. Britain can thank its steam engines. Its heightened vibrational energy transmits kinetic buzz to colder molecules in a cascade of dissipation. Harnessing the heat energy is not the easiest thing to accomplish. According to Marlowe, capturing heat for useful mechanical purposes has been a constant challenge. Recently, a team of scientists devised a clever way to squeeze additional energy from low-grade thermal movements, and the result could soon become coming to a sewage treatment plant near you. This shows that scientists have been having a hard time harnessing the energy. However, they are finally getting close to capturing it. Marlowe also states, and now Bruce Logan and Raby have found a way to boost fuel cell voltages by using microbial waste heat. It starts with thermolytic solution, ammonium bicarbonate, in initial experiments that metabolic heat splits into positively charged ions and negatively charged anions. A stack of ion exchange membrane shuttles anions toward the electron accepting electrode, and cations toward the opposite electrical pole. This process is called reverse electrodialysis, and it's a clever way to produce something from what has typically been neglected as nothing. Initial experiments show power densities several times higher when thermolytic solutions and ion exchange membranes are used. Logan, for his part, is bullish on the technology's potential. Just the energy in wastewater alone in the U.S. is somewhere between 15 and 20 gigawatts, or the equivalent to 15 to 20 nuclear power plants. This is an excellent example of how much energy can be harnessed from heat to power the world. If just by capturing heat energy from waste plant can equal the power produced by 15 to 20 nuclear power plants, and the opportunities for heat energy are endless. And this is an example of a waste plant that you could produce energy from. Thermoelectrics. Electricity is considered a high-grade energy because it can be converted into other forms of energy for use and storage without significant losses. Thermal energy lies on the opposite end of the spectrum. It is a low-grade energy, which means that attempts to transform heat back into other forms of energy is only an option in certain regions of the globe. Most of the time, thermal energy is written off as waste heat and released into the environment without further ado. But scientists like Jonathan Pfluger are working on converting thermal energy back into high-grade energy. Pfluger is a graduate student in Wolverton Lab at Northwestern University. According to Pfluger, he works at the intersection of computer science and quantum mechanics and energy materials. He is part of the large-scale collaborative effort at Northwestern to design and improve upon material systems and energy conversions using the power of computers. Pfluger works on thermoelectrics, materials with curious links between thermal and electric realms. By connecting a battery to a block of thermoelectric material, the block will produce temperature gradient. One side will grow warmer than the other. Conversely, heating up and cooling down one end of the block will cause the block to produce an electrical voltage difference. By adding heat, the block can now act as a battery. Imagine the potential of thermoelectric power devices. One could charge a cell phone by using just body heat. Work being done by Pfluger is just another way of showing the endless possibilities behind heat energy. And this is an example of a light bulb with a flame inside showing off the amount of heat it would let off. Thermogalvanic effect is another way of harvesting heat energy. Large amounts of heat are lost every day throughout many different processes, but the largest cause of lost heat is industrial processes. Researchers at MIT and Stanford have found a way to collect the energy and turn it into useful energy, such as electricity, using a process called thermogalvanic effect. According to the article, to begin, the uncharged battery is heated by the waste heat. Then, while at the higher temperatures, the battery is charged. Once fully charged, it is allowed to cool. Because the charging voltage is lower at high temperatures than at low temperatures, once it is cooled, the battery can actually deliver more electricity than what was used to charge it. The extra energy, of course, doesn't just appear from nowhere. It comes from the heat that was added to the system. The system aims at harvesting heat less than 100 degrees Celsius, which accounts for a large portion of the potentially harvestable waste heat. In a demonstration with waste heat of 60 degrees Celsius, the new system has an estimated efficiency of 5.7%. This shows how you can collect heat that would be wasted and use it to heat the battery, then charge it to the following that, the battery would have more power than it would with just regular charging. While the new system has a significant advantage in energy conversion efficiency, for now it has a much lower power density, the amount of power that can be delivered for a given weight, than thermoelectrics. It will also require further research to assure reliability over a long period of use and to improve the speed of battery charging and discharging. And this shows an example of the battery charging. You would heat in step 1, then step 2 is the charging, step 3 you cool it down, and step 4 is discharging. High throughput energy. Another way of harvesting energy is through high throughput energy. But new research points the way to a technology that might make it possible to harvest much of that wasted heat and turn it into usable electricity. That kind of waste energy harvesting might, for example, lead to cell phones with double the talk time, laptops with computers that can operate twice as long before needing to be plugged in, and power plants that put out more electricity for a given amount of fuel. This once again shows how much heat energy can significantly increase usage time and battery life. Hagelston says that with present systems, it's possible to efficiently convert heat into electricity, but with very little power. It is also possible to get plenty of electrical power, which is known as high throughput energy, or high throughput power, from a less efficient, therefore larger and more expensive system. It's a trade-off. You either get high efficiency or high throughput. But their team has found a new system that would make it possible to get both. A key to the improved throughput was reducing the separation between the hot service and conversion device. And this is an example of a cell phone with its battery out to show an example of charging it and it being double as charged. The last, which is what I referenced at the start as the most effective, is the power card. Matt Skolin thinks there is, and he's formed a company to prove that idea into reality. The key to Skolin's plans is through something called thermoelectrics. A thermoelectric is a material that turns heat into electricity. Skolin believes he can take all the wasted heat and turn it into energy very similar to the way solar panels work. The cool thing about this power cord is that it's like a cell. You can almost think of it like how a solar cell is with the sun. You can put one in the sun and get a small amount of power. You can put a square mile of solar cells out in the sun and you got a power plant. Skolin says it's the same with these thermoelectric power cards. If you've got a large waste heat source like the exhaust stack of a coal burning power plant, then you string together a lot of power cords, but if you don't have that much heat, you only use a few of them. This is a perfect example of how his power cards working the same as solar panels and being able to achieve the same effect. He hopes to grow his company into being able to harness energy from people and businesses as well. He acknowledges right now thermoelectrics are a tiny part of electricity generating market, and Skolin knows he's facing a lot of hurdles to get people to try his new technology. He stays excited because he gets to work, geek out all the things about this, which is what he's really passionate about. Skolin's goal is to make the power card the power source all around the world. And that's an example of his power card, which will be the future of energy. And these are the references used during the presentation. Thank you.